Now, to get the bending moment at D, as we discussed, we should do a section at this level, and then we'll keep the right point. The distance from D to B is equal to the total length of the beam, which is 1 meter, minus A. And now we can do some of moments about D to get the expression of the bending moment at D. So let us represent first the section. This is the section. We have V is upward to rotate clockwise about the extremity. MD is positive clockwise to compress the upper part. To get the bending moment at D, we do sum of moments about D equals to 0. Why we select D to not have to calculate the shear? Okay, because when you do sum of moments about D, the shear will not have any moment. So we have taking the counterclockwise direction as positive for the sum of moments equation. You have a minus MD, and you have the moment of K, which is also clockwise. So minus K, which is 480 times 1 minus A equals to 0. So if you look at the expression of MD, you can see that larger the value of A, smaller is MD. And smaller the value of A, larger will be MD. So we said that A is between 0.5 and 1. If we increase A, okay, this will increase the value of MC. And if we decrease A, this will increase the value of MD. So whenever we have one of these scenarios, we'll have a larger maximum because we are favoring the increase of one of the two bending moments in absolute value. So in order, if you want to have a minimal absolute value, this will correspond to the value of A, for which just we have the absolute value of MC is equal to the absolute value of MD. We know that MC is a positive and MD is negative. So we can say that the value of A, which will minimize the absolute maximum value, is the one corresponding to MC equals to minus MD. So you have already found the expression of MD as a function of A. So minus MD is 480 times 1 minus A. And MC is 480 minus 360 over A. By equating them, we ensure that we have equal values of maximum positive moment and maximum negative moment. However, if we deviate from this value, if we increase A, then what will happen is that this value will increase. And if we decrease A, then this value will increase. So in both cases, we are deviating furthermore from a minimal possible value. Okay, so by setting minus MD equals MC, you just get the minimum possible absolute value of the maximum moment, because if I deviate into any direction from this optimal value, one of the two bending moment will increase. Okay, so I can say that this equation minus MD equals MC will give me the value of A, which will minimize the maximum absolute moment. And this will give me, when I replace A by its value, I will get that MC in absolute value equal to MD equals to 64.31 Newton meter. So this is the minimal maximum I can reach. Now, based on this, they are asking us to find the corresponding maximum normal stress due to bending. If I look at my cross section, I have a rectangular cross section. For this rectangular cross section, I know that S is equal to I over C. If I replace I by BH cube over 12 and C by B over 2, I get that the corresponding expression for my modulus S is BH square over 6. So now calculating S for my beam and knowing the absolute value of the maximum bending moment, I can determine the maximum normal stress. The maximum normal stress is equal to the maximum bending moment over S. And here, as we discussed before, since C1 equals to C2, then I just have to determine the absolute value of the bending moment the maximum of the absolute value. I don't care if I have its intention or compression, because C1 and C2 are equal. But if C1 and C2 are different, then as we discussed before, we should differentiate several cases. We should take the case of maximum positive bending moment alone, maximum positive negative moment alone, and to see here they are equal, because we designed, if you want any way to have the maximum positive moment equal to the maximum negative moment. But in general, whenever we have C1 different than C2, I should do several cases to determine which is the most critical one. So here, I don't have this issue because already C1 equals to C2 and my maximum positive is equal to my maximum negative moment. So the maximum normal stress is equal to the absolute value of the bending moment maximum over S. Another design problem. In this problem, we want to draw the shear and bending moment diagrams for the following beam and to determine the maximum absolute value of the shear and the bending moment. I keep this problem as a practice for you. I want to give you a hint. Whenever here you have this cable, you have a cable here. So you have a tension in EF, and you have a pin at A. So you have a X and a Y. You have three unknowns as external reactions. You can calculate them. You have to write three equations: sum of X equals 0, sum of Y equals 0, and sum of moment about A, for example, equals to 0. Once you get your external reactions, this eccentricity of the cable can be replaced by, at point D, a force and the moment couple. Okay, because the idea is how this tension will affect the shear and bending moment diagram. This tension is creating a couple about point D, because you have a certain distance between the tension and point D. So you can replace TEF, you can move it from F to D. If you move from F to D to have equivalent result, you should add the couple it's creating about D. Another method of thinking is to say I have the tension here at this level is TEF. So if I put at D, if at point D I put a positive force T and a negative force T opposing each other, TEF, TEF, then this is equivalent to a force and decouple at dy, because these two forces are opposite in sense, but they have equal magnitude, so they can be replaced by a couple at D. So the couple at D, M at D, can be written as tension times distance times this distance D. Okay, so now you can replace your, if you want, your beam ACDBE by a beam ACDB, and at point D, you just have to put a force of 240, which is equal to the tension in the cable, and the couple that you can calculate as T times D. And once you have this, to draw the shear and bending moment diagram, you can use or section method or area method. And of course, pay attention here that you have a couple, since it's a counterclockwise couple. So whenever you draw the bending moment diagram, pay attention that at D you have a downward jump, because when you move from A to B, a counterclockwise moment will cause a downward jump in shear, in moment, sorry, diagram. So you can check this here. Okay, this is the downward jump in bending moment. And as expected, as we discussed before, the couple, you cannot see it in the shear diagram. This is why when you draw bending moment diagram, look at your shear diagram and look at your beam to know if you have couples or not. Okay, so try to practice area method and section method using this problem. Now let us continue with design problems. In this problem, we want to draw the shear and bending moment diagrams for the beam and loading shown and to determine the maximum normal stress due to bend. Again, because we talked a lot already about details of shear and bending, just try to draw the shear and bending moment diagrams and verify that you are able to compute the actual profile. Now, once we have the diagrams, in order to find the maximum normal stress, all we have to do is to apply the formula that sigma is equal to m over s. And here we have a rectangular cross section. So, and T1 is equal to C2. So the maximum normal stress in compression is equal to the maximum normal stress here in tension. And we can consider that if we, after plotting the diagram, okay, after plotting our diagram, you can see that you have a maximum positive moment of 50.7 and a maximum negative moment of 15.96. Now, as we discussed, since C1 equals to C2, so you just take the maximum absolute value, which is 50.7, and then you can calculate the maximum normal stress for tension and compression as sigma equal to m over s, where s is calculated as bh square over 6 because it's a rectangular cross section. So also this problem can be used as practice because it's the same concepts that are repeated. Let us do something new. In the following problem, we have a beam for which we want to determine the size. We don't know the size. It's a square cross section, but the length size is unknown. Okay, so the length of each of the side of our square is not known. We want to determine the value of A, knowing that the material used has an allowable normal stress of 12 megapascal. Now, when they don't differentiate between tension and compression, so we just consider that they are equal if you want. The allowable normal stress in tension and compression is 12 megapascal. And again, here, because of the symmetry of the cross section, C1 is equal to C2. So also I don't care if whenever I have C1 equal to C2, so the maximum value of tension is equal to the maximum value of compression taking place. And then all I have to do is to be able to design what should be A, is to draw the bending moment diagram of my beam, determine the absolute value of the maximum bending moment, and say that sigma is equal to absolute value of m max over s. Okay, here, since I have an allowable value for normal stress, this will correspond to a minimum value of s. Okay, so to not exceed 12 megapascal. So when I reach sigma allowable, which is 12 megapascal, this will correspond to the minimum possible value of my modulus S. Okay, so I want first to get the maximum bending moment. Use this formula to get S minimum and express as function of A. S is, you can easily express as function of A because here it's a square. The inertia of a square is, you can deduce it from a rectangle, bh cube over 12, but here b is equal to h. So it's a to the power 4 over 12. And for c, c1 equals to c2 equals to, the neutral axis is at the middle, So you have the distance from neutral axis is A over 2. And now your modulus S is I over C. So it's equal here to A cube over 6. Okay? And then when you get S minimum, you can get the corresponding A minimum. So S minimum corresponds to A minimum cube over 6. And then you can calculate the minimum value of A to not exceed the allowable normal stress of 12 megapascal. Now, here, what do we have? We have a fixity. We have a fixity at A, okay? And we want to draw the bending moment diagram to know where is the maximum bending moment. Here, if you want, you can know by small analysis where the maximum bending moment will be. Okay, let us do it together. First, in this part, you don't have a bending moment because if you do a cut here, you don't have anything. So bending moment at B is 0. And if you do a small figure, okay, you can see that the larger distance from B. So if you do a section, higher is this distance, larger will be the bending moment. So you can say that the maximum bending moment is taking place at A. And therefore, no need here to draw a diagram. You can just, by a small analysis, say that the maximum bending moment is taking place at A. So let me determine, if I do a section just here, and I reject the fixity part, I get the following. I have, this is AB, and I can replace now the distributed load by a concentrated force. Okay, this concentrated force is at 2/3 from 2/3 from B, 2/3 of 1.8. So the distance here is 2 times 1.8 over 3, which is equal to 1.2. Okay, and it is at a distance from A equal to 0.6. So now you can say that the value of this force is equal to the area of the triangle. The area of the triangle is 18 times A 1.8 over 2. So you can deduce that the value of the bending moment at A is equal to this force times this distance, which is 0.6. So this is how you can get the maximum bending moment in your beam. Okay. Now, once you get the value of this bending moment, which is 9.72 kilonewton meter, you can get the minimum value of your modulus S. So S minimum is equal to the maximum bending moment over the allowable stress. These two are known now because we calculated M max and sigma allowable is given. Now for units, we use for M Newton meter. So make sure to convert to Newton meter, and sigma is in Pascal. Then you will get S in meter cube. And as we discussed, S minimum corresponds to A minimum. So you can calculate what should be the minimal value of A to not have a rupture. Okay. So this is how we can design the minimal size of the length of the square side in order to not have rupture. Another design problem